Well, hey, all you junior wilderness explorers. Today we're going to talk about the logistic equation. There's a couple of variables here in the logistic equation. The first thing is R. And obviously, R is going to stand for the rate of growth. Okay, and then P often stands for the population. Okay, and then K stands for the, I don't know why, there's two C's here, stands for carrying capacity. And we often use this equation for population of wildlife, perhaps. Sometimes they talk about this maybe being a learning curve where the population might be how many answers you get right on a 100-question test. So K would be 100 then. It might be that this is the number of people that know about a rumor. So there's a couple different typical examples that we see when we use the logistic equation. Let's look at an example with a population of deer. So here's the example. We have a population of deer of about 900,000 in the state of Kentucky. The rate of growth was estimated to be 23.11%, which somehow they calculated to be the natural log of 2 divided by 3. And the carrying capacity, so the maximum number of deer they felt like they could feasibly manage and feed on the state of Kentucky was 1,072,764 deer, right? And so let's first of all set up the differential equation for this example. And so that looks like this. And we know that this has an initial value of 900,000. So let's go about solving this differential equation. So first of all, notice that this can be separated. So we're going to move, let's simplify this first. And so when we simplify it, we get, so hopefully that's not too bad. But then what we're going to do is we're going to divide the p's, the expression of p's right here. We're going to put them over here, and the dt is going to come over here. And so when we do that, it looks like this. And so in order to do this, this right here, this part right here is going to be a little bit of a challenge. But we can use partial fraction decomposition to come up with this integral. And I'll leave it to you, to determine whether or not that's correct. But notice now we know how to integrate those two parts. And so we get, when we integrate, we get this. And with constant apologies, if you did try to work this out, I messed this up. That should be a big old plus sign right there, which then that translates to this negative right here because we have that negative right there. All right, so now if we're going to go about solving this, that looks like fun, doesn't it? Okay, so how are we going to solve this? Let's move this over to that side. Okay, and when we do that, we get this. And notice I have adjusted this. So this right here, when we subtract two logarithms, it's the same as dividing. Okay, one log or inside one logarithm. So this makes it a little bit nicer. And now we raise both sides to the e power, and what we get is this. And so there we go. And I'm taking a lot of liberties. Try not to take as much of your time. If things don't make sense, please, 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 please make sure you pause the video and try to work that out yourself. All right, so now we're trying to solve. We have a p here and a p here. So I'm going to have to take this and move it to that side. And so what that looks like is this. And distributing, we get. All right, and then we're going to add that to that side, so we get the p's together. And at this point, we can factor out the p. And at this point, we have one step left to determine what p is. So if we divide by this phrase here, we get that P equals, and here we go. And so now it's left to determine what the value of C is. All right, so when we try to find this value of C, we're going to plug in, remember our initial value is this is 900,000 when T equals 0. So let's look at that. And we get this equation. Notice that e to the 0 is 1. And so we have this right here. Okay? 1,072,764 C divided by 1 plus C equals 900,000. And so it can be shown that C equals. So there's our value for C, which we can plug back in to these C values here. And so finally we get an answer of you see what's going on here. You see we started here at 0 at roughly 900,000, and that's because this number here isn't exact right there. And we get to where we're increasing, and you see that our biggest value is going to hit 1,072,000 here sometime. And each of those numbers down here at the bottom are the years. Okay, and so there you go. We never quite get to that 1,072,000. So let's take a look at what other questions the book might ask us. So the book may ask us, come on, here we go. What is the deer population in 3 years? Now we looked at the graph and we could see that. But if we go to Desmos, we can adjust this. And let's ask Desmos to calculate that, to calculate P of 3. Well, where is your answer? About 975,765 deer. So let's see if I remember that. 975,765 deer. So you could use that equation pretty easily and figure that out. Okay. So let's take a look at the general rule for this. And so from our textbook, the general rule for solving the logistic differential equation is that. And so you can see here with our deer population, the population is the 900,000 there times this, the K minus the initial population. And we didn't exactly show that in our solution, but I think it'd be pretty easy to see that. Now, don't tell anybody, but apparently this enjoys playing a little poker on the side to the teeth power there. All right, anyway, hopefully you kind of make sense of what's going on here. We'll talk about this obviously more in class. We'll see you then. Thanks for watching.